In this example, we will learn to find the local minimum and the local maximum using the first derivative. So first, let's take a look at the local minimum. A local minimum is the lowest point in an interval. This is when the graph turns. So if you look at the slope of the tangent line at any point to the left, that slope is going to be negative. If you take a look at the slope of the tangent line on the right, that slope is going to be positive. So when the slope of the tangent line, or the first derivative, goes from being negative to positive, we have a local minimum. The function is decreasing. In other words, the slope of the tangent line is negative. Then we hit a local minimum, and on the other side of it, the function is increasing, which means the slope of the derivative, or the slope of the tangent line, or the first derivative, is positive. Let's take a look at the local maximum. Local maximum, on one side of it, the function is increasing. Then it hits a maximum, and then the function starts decreasing. Now, when is a function increasing? A function is increasing when the slope of the tangent line is positive, and it's decreasing when the slope of the tangent line is negative. So when the first derivative goes from being positive to negative, that means we have a local maximum. But again, for that, we need to first calculate what the first derivative is and what the critical points are. So our function is f of x equals 2x cubed minus 30x squared plus 126 plus 5. And in order for us to figure out the critical points, we need to look at this. Where is f prime of x equals to 0? Where is f prime of x undefined? Those are always the two requirements for us to have a critical point or a critical number. So f prime of x, 3 times 2 is going to be 6x squared minus 60x plus 126. This cannot be undefined because we're not dividing by a variable at any point. So we can set our first derivative equal to 0. And to make this easier, let's divide everything by 6. So we're going to get x squared minus 10x plus 21 is equal to 0. If I factor this, this is x minus 7 times x minus 3 is equal to 0, which means my critical numbers, my critical values, are going to be x equals 7 and x equals to 3. So one of these is going to be a local minimum, one of these is going to be a local maximum. I got to figure out which one's which. So I'm going to look at the first derivatives and do the first derivative test. So this is our number line. We have x equals 3, x equals 7. These are the critical numbers. So these are the turning points. First thing, I'm going to label the interval. So this interval is negative infinity to 3. The second interval is from 3 to 7. And the third interval is from 7 to infinity. Let's pick a test point. So I can pick anything to the left of 3. For the sake of simplicity, I will pick x equals to 2. In the middle, between 3 and 7, I can pick anything. I'm just going to pick x equals to 5. And to the right of 7, I can pick anything. I'm just going to pick x equals to 8. Okay, these are my 3 test points. Once I have a test point, I want to see, is my first derivative positive or negative? Because when the first derivative is positive, the function is increasing. When the first derivative is negative, the function is decreasing. So we're going to take the first derivative, which is 6x squared minus 60x plus 126, and we're going to put that in Desmos. And then we're going to figure out what is f prime of 2 equal to. So f prime of 2, this is equal to 30, which means f prime is positive. F prime of 5 is equal to negative 24. Okay, so here the first derivative is negative. When x equals 8, f prime of 8, this is equal to 30. which means the first derivative is positive. Now we're going to look at the behavior of f of x. So if the first derivative is positive, that means this function is increasing. Negative, function is decreasing. Positive, the function is increasing. So here's kind of, I'm going to do a quick sketch of the function. So the function is going to be increasing, increasing, increasing. It's going to hit this point, which is x equals 3. Then it's going to decrease, decrease, decrease. It's going to hit this point, which is x equals to 7. And then it's going to increase, increase, increase. So x equals 3, this is going to be a local maximum. X equals to 7, this is going to be a local minimum, because the function increases, increases, hits the max, and then it starts decreasing. Then it decreases, decreases, hits the local minimum, and it starts increasing. So the local minimum is going to be at x equals 7. The local maximum is at x equals to 3. To find the value of these, we simply take x equals 7, plug it into this function, take x equals 3, plug it into this function. Once again, I do recommend you use Desmos or a calculator and not do it by hand. This will give us 103, and this will give us 167. So the local minimum is going to be the point 7, 103, and the local maximum is going to be the point 3, 167. Okay, next example. This function has one local minimum and one local maximum, which we want to find. So let's go through this one a little bit more quickly. All right, first thing we need to do is we need to find out what is f prime of x. So f prime of x, the derivative of 1 is 0, it's a constant. Derivative of 5x is going to be 5x. The negative 1 times 80 is negative 80, x to the negative second. So if I rewrite that, I'm going to get, I'm sorry, this should be 5, not 5x. I'm going to get 5 minus 80 over x to the second power. My critical values are my turning points. So how do I find my critical values? F prime of x has to either be 0 or f prime of x is undefined. Now I know for sure that f prime of x is going to be undefined because I'm dividing by a variable. So if x equals to 0, then f prime of x is undefined because you'd be dividing by 0. So this is one critical value. The other critical value is going to happen when f prime of x, which is 5 minus 80 over x squared, when this is equal to 0, we will have the other critical value. Now we're going to clear the fraction. So remember, to clear the fraction, we need to multiply each term by the least common denominator. The least common denominator is x squared. So we're going to multiply the 5 by x squared, the 80 by x squared, and the 0 by x squared. Okay, so if we keep going, 5 times x squared is 5x squared. This divides to 1. That's the whole point of clearing the fraction. So we get 5x squared minus 80. 0 times x squared is 0. I move the 80 to the right. So I get 5x squared equals to 80. Divide by 5. X squared is 16. Square root both sides. And I get x equals to plus or minus 4. So my critical values are going to be 0, negative 4, and positive 4. All right, let's go ahead and do the first derivative test. So for the first derivative test, we're going to have our intervals. We got negative 4, we have 0, and we have positive 4. So split these up. First step, label the intervals. The first interval is from negative infinity to negative 4. Second interval is between negative 4 and 0. The next interval is between 0 and 4. The next interval is from 4 to infinity. Okay, now let's go ahead and pick a test point in each interval. So to the left of -4, we could just pick -5. Between -4 and 0, we can pick -2. Between 0 and 4, you could pick +2. And then to the right of 4, you could pick 5. Okay. Once we pick these points, we want to look at, is the first derivative positive or negative in each of these test points. So we want to look at f prime of x. So f prime of -5, once again, you would put the first derivative function in Desmos, and then just do f of -5, f of -2, 2, 5, etc., etc. So f prime of -5, this comes out to be 1.8, which means f prime is positive. If f prime is positive, then the slope of the tangent line is positive, which means the function is going to be increasing. For -2, we get f of -2 is equal to -15. This is negative, so the slope of the tangent line is going to be negative. For f of 2, we are going to also get -15, which means the slope of the tangent line is negative and the function is decreasing. And lastly, for f of 5, we get positive 1.8. So this is first derivative is positive, which means slope of the tangent line is positive, and the function is increasing. So here, the function is increasing. Here, the function is decreasing. Here, the function is decreasing. And here, the function is increasing. Okay, so now let's make a conclusion about f of x. So f of x is increasing, decreasing, decreasing, and increasing. All right, let's do a quick sketch. So the function is increasing, increasing, increasing. Then it's going to hit this point, which is -4, and then it starts decreasing again. Here, the function is decreasing, decreasing, decreasing. It's going to hit +4, and it's going to start increasing again. So this point, x equals to -4, this is going to be our local maximum. This point, x equals to +4, this is going to be our local minimum. Okay, so our local minimum is going to be at x equals to 4, and the local minimum is going to be 41. Now remember, to get that, you would take 4 and plug it into the original f of x function, not the first derivative. To get a y value, you plug in x into the original function. The local maximum is going to happen at x equals -4, which is here, and the local maximum is going to be -39. Now, it might be kind of weird to see that the local maximum is actually less than the local minimum, but remember, our local maximum and minimum are turning points. So this means that only within this interval, this is the highest point, and within this interval, this is the lowest point. That's all this is saying. And if we graph this function on Desmos, which I will attempt to do quickly, we got f of x equals to 1 plus 5x plus 80x to the -1st. Here's what's going on. This point here, -4 comma -39, this is locally, this is the highest point. Therefore, it is the local maximum. This point, which is 4 comma 41, locally, it's the lowest point within this interval here. So this is going to be the local minimum. We have one more example left, but we can cover this example in class. This one will go by pretty quickly.